Well, thank you very much for the invitation to present this afternoon. This has been a nice opportunity for those of us who've been involved in looking at research related to cumulative effects over the last year, even when we weren't necessarily calling it cumulative effects. And this afternoon, I wanted to talk about some work that we've been doing over the last decade in a series of different cycles of the GSC's environmental geoscience program, but really all focused around the issue of critical metals. Most of you, I'm sure, have certainly seen plenty of coverage of Canada's discussions about critical minerals and our discussions with the US over the last couple of years on securing North American supplies of some of these really important resources. And just earlier this month, in fact, actually our minister announced the country's first ever list of official critical minerals at the PDAC conference. And so this research is certainly showing up in many places. It's something that the general public are becoming more familiar with, and a really nice opportunity for us to highlight some of the work that we have been doing to really understand how can we develop these resources domestically in a manner that's environmentally responsible, and that might actually distinguish Canada as a particularly reliable and environmentally responsible supplier of these resources. So this afternoon, what I wanted to do was talk just in general terms. For those of you, I realize that not everybody on this call is necessarily a geologist or a geochemist. So I wanted to talk just a little bit about how we kind of got to this point where we're seeing a lot of discussions about critical metals, even in the national media. Talk a little bit more specifically about what the resources look like in Canada, and this is really a prelude to Chris Lawley's presentation that will follow my own about what the GSC and our international partners are doing really to try and better define where these resources exist. And I'm going to end with sort of a coverage. It's just be a really high-level overview of some work that we've been doing to study especially niobium and rare earth elements in Canada, and one of the most common type of deposits called a carbonatite. So we focused on a study recently in Oka, Quebec for that. And then I will discuss our ongoing research, which is in Cobalt, Ontario, where some of you might be aware that there has been a lot of intense interest recently in mining cobalt, an essential component of rechargeable batteries, to help fuel things like the electric vehicle boom that is currently going on. And it's causing a lot of new interest, but also some concerns in an area that historically was a very important silver mining district, but which might see renewed mining again for cobalt. So I wanted to start just very generally, so that, this is something I like to give in talks, particularly to the public, just to kind of give people a sense of how do we get to where we are today, and why is it so challenging for people to understand what their stuff is actually made of. If you go back into history, even as far back, let's say, for example, as 8000 BC, that was really when we first had the sort of first recorded usage of native metals, where people were actually using things like gold and obviously amber, jade, basalt, and other things to make various tools or weapons or other things that were important at that point in human history. And then, of course, we had things like the copper, bronze, and iron ages, where, humankind's use of these resources started to expand as we discovered new things and how best to use them in our daily lives. And then it really wasn't until the scientific and industrial revolution, let's say in the late 1700s through the 1800s, where we really started to see a lot more usage, much more of a diversity of elements show up in our everyday items. But really, it's in the last 20 years, in particular 20 to 30 years, the periodic table has expanded very, very rapidly. And we've gone from a period back in the 1960s when most of the resources that were in our households might be just sourced at a local quarry or other location just down the street. Whereas now, of course, even in our modern cell phones, we've got probably 60 plus elements in a given cell phone, and those are sourced from countries all around the world, including elements that some of us might actually have a challenge pronouncing and certainly discussing where they actually come from and how they're important in our cell phones or other technologies. So this is just a quick overview of what you see a variety of different names that are used for these critical minerals. Some of them are also referred to as technology critical elements or just simply rare elements, and sometimes strategic metals, especially for those that have important military applications. But the term critical in particular really denotes the fact that they're in high demand and there's some sort of perceived risk to their supply. So that could be a geological risk, like they're very scarce and they only occur in the crust in mineable concentrations in very few areas. It could be a geopolitical risk or other reasons, but there is some risk to our continued supply going forward. So, the elements that have received the most attention over the last decade are the rare earth elements down here on the periodic table at the bottom. And they're typically, this definition varies a bit, but they're typically divided into light rare earth elements from lanthanum through to gadolinium, depending on whose definition you're using. And then we get into the heavy rare earths, all these ones shown in green here, going from either europium or gadolinium all the way up to lutetium. And the heavy rare earths are actually considerably less common, and in fact they're all only produced in one country, in China these days, and are especially valuable for our modern technologies. So I've picked a variety of these technologies to sort of show around the borders of this slide, but we're also looking at other elements that we've become very reliant on. So these include, for example, some of the semiconductor metals, things like gallium, germanium, antimony, and indium. Cobalt, obviously really, really important for battery usage these days. These are the platinum group metals shown in purple in the center of the diagram, so important for a fairly wide variety of applications. And unfortunately, you see a lot of things like catalytic converter thefts going on these days because the price of these elements, like rhodium and palladium, is so high that it actually, there are people that are trying to take advantage of the situation and sell these on the open market. And then obviously you've got other elements like lithium, again, a very important battery metal, and all of these things are definitely on the government of Canada's radar screen these days for further development and hopefully in increased domestic production. So if we look at things, like our gadgets that we have in our homes, in our pockets, all of these low carbon, green energy applications, these things are full of all sorts of rare metals. And so if you just look, for example, at your smartphone that most of you probably have close at hand there, we've got some more common components, things like silicon that are made to produce the glass, for the screens in these phones. But all of us take, for example, we take for granted that we can just swipe our finger back and forth, and that ability to interact with your phone is actually mostly due to indium. It's a transparent conductor, and it allows us to actually interact with our phones, just by swiping our finger across. An element like cerium is used to buff the glass to that very, very high polish. And then we've got a wide variety of elements, yttrium, lanthanum, praseodymium, other rare earth elements that are used to produce these beautiful colors that we all enjoy in our screens these days, whether it's our cell phones or our brand new, LED TVs and such. And then electronics, they've got, again, a whole wide variety of different elements. That vibration we get says, hey, you've got a message on your phone. Those are little rare earth element batteries vibrating in our phone. And then we've got the batteries themselves, obviously. We've got things like lithium and cobalt. And actually, I mentioned when I talked about vibrations, I meant to say magnets that are actually vibrating. So even when we use our headphones or, if we've got little earbuds and that, it's these little magnets that are actually that are vibrating to produce that sound in our ears. And elements like neodymium, for example, are really, really crucial for that. And then over here on the right, we've got things like electric cars. I pulled the statistic out recently. If you look at each Toyota Prius, for example, there's about 20 to 30 pounds of lanthanum in that car associated with the batteries. Wind turbines, obviously just an essential component of our transition to lower carbon energy sources. And a single 3 megawatt wind turbine can use up to 2 tons of rare earth element magnets. And so it's actually these magnets, instead of gears, passing one another inside these wind turbines that actually give us the ability to translate that wind energy into electricity. And again, these rare earth elements, are absolutely fundamental to the process. So various countries over the last decade in particular have developed what they call indices of criticality, or developing, just some sort of index to rank various elements in terms of how critical are they. And so I mentioned Canada just officially released its first ever list earlier this month, but there's been a few other countries. For example, here, the British Geological Survey released one of these indices back in 2015, the US DOE in 2011. And so, they rank elements from sort of high to low in terms of their risk. And so rare earth elements are almost invariably near the top of these lists. And one of the main reasons is that, the leading producer is China, the top reserve holder is China, and, 80 or 90% of the production happens in a single country. And I don't think it's a surprise to anybody that, there are a lot of geopolitical concerns about having that in a single country, particularly in a country like China, where there have been some issues related to trade. In fact, actually, a lot of our research was related to a simple argument that actually emerged between China and Japan back in 2010. It was actually over a fishing dispute where the Chinese decided to suddenly cut off their exports of rare earth elements to Japan. This was just a territorial dispute in 2010, but it caused the prices of rare earth elements to suddenly just go through the roof. Some of them increased within, a week or two to more than 400% of its previous price. And this is what really initiated a lot of this concern about the security of these supplies, and got a lot of countries, including Canada, looking for domestic sources. And then we've got other elements. I won't go down through this list, but things like cobalt, lithium, and even we've spent a lot of time thinking about niobium, an element some of you might not be that familiar with, but it's an absolutely fundamental component of high strength, low alloy steel. So, this is the kind of steel we need for applications like in aircraft engines and other things where you need high strength but very low weight. I read a stat recently also where, for example, if they had built the Eiffel Tower today, they could have used roughly about 7 times less steel just by adding like a very, very small percentage of niobium to increase the strength of that steel but decrease its weight. And then over here on the right, this is, for example, if you're looking, primarily at something like clean energy, this is a matrix showing the importance to clean energy on the y-axis versus supply risk on the bottom x-axis here. And the elements that are most critical are all rare earth elements in this case, and that still persists even today. These are elements where we're still looking for supplies, particularly supplies out of outside of China, but other elements like lithium and tellurium and others, if you're really concerned primarily about energy sources, these are things that are really fundamental to those technologies. So we know there are elements where demand is definitely predicted to exceed supply over the next 10 to 15 years. Here's a list on the bottom, especially heavy rare earth elements. There's no heavy rare earth element producers at present outside of China. And even for an element like niobium, the demand for ferroniobium, it's so important for a lot of development that its demand is forecasted to grow at more than 8% per year. And so, you can appreciate that this certainly places a strain on our existing supplies. So just in terms of where do these elements come from at present, these are some data that I pulled together a few years back, but it shows, for example, elements like cobalt. The world's leading producer of cobalt is actually the Democratic Republic of Congo. And a portion of that, roughly 50% or so, is produced in large-scale mines, quite often run by Western mining companies. But a significant portion of that supply is also run in small-scale artisanal mines, many of which actually employ child labor and have other serious issues where they're run by militias and are actually used, for example, to fund various conflicts that are going on in the Congo and the surrounding region. And so this has caused companies like Apple and Samsung to look very, very carefully at where they get the cobalt for their batteries. And there's been a lot of groups, certainly like Amnesty International and others, that have really done a good job of highlighting these concerns. And it does present an opportunity for countries like Canada. We certainly do produce some cobalt, but we could potentially produce more on the world market and alleviate some of these concerns over things like child labor and such. An element like lithium is mostly produced in places like Australia and Chile, but again, there's even some environmental concerns in places like Argentina and Chile. A lot of this lithium is produced from brines way up in the Atacama Desert, and there have been concerns over things like groundwater contamination. Certainly, companies, not necessarily respecting the land rights of indigenous populations and such. And so, these are concerns. We all need to think carefully about this footprint that's associated with our use of these resources. Certainly, rare earth elements are a fairly extreme example. Back in 2016, China produced about 83% of the world's supply of rare earth elements. The US is actually producing some from a mine called Mountain Pass in California these days, but they're still produced. They're shipped overseas to China for production. So it's one thing to find a resource; it's another entirely to actually separate those rare earth elements from one another, and that's still an ongoing challenge that we really need to spend a lot more effort perfecting here in Canada. And then Australia and Russia are a couple of other producers there. And finally, I threw niobium on the list here because we've done some research on that, but it gives you a good example. There are a couple of deposits in Brazil that constitute more than 90% of the world's supply. And the other main producer of about 9% is actually Niobium mine up in the Saguenay region in Quebec. And, again, this is a situation where if you do have some challenges, they could be geopolitical, for example, with the Brazilian government, it would really put, a damper on the world's niobium supply. And it's a very essential element for a lot of different uses. So the other thing that I wanted to communicate here is that it's not just about these rare metals, and actually many of you have seen, for example, copper is a fundamental part, obviously, of any electric car, and certainly all of our computers and other technologies. And if you look at production, it's not as if we're about to run out of copper anytime soon, but if you look at the growing demand of copper going back, for example, all the way to 1900, you can just see how it's really accelerated. I think this plot was originally created based on data around 2010, but the projections show that there will be at some point or another, going, perhaps sometime around 2040, a point at which our existing resources of copper and our ability to produce it from deposits in countries, for example, like Chile, which really dominates that supply, they're really going to be restricted unless we identify new resources. We certainly have to get much better at recycling stuff like this on the right, our electronic wastes. And, we will probably have to look at some substitutions to slow that demand unless we really are prepared to open up, new copper mines all over the place and really increase our rate of production. So here's a really nice graphic that was released earlier this month. This was just announced again by Minister O'Regan on March the 11th of Canada's official list of 31 critical minerals. It's actually larger than 31 because it includes a couple of groups, including, for example, like the rare earth elements and the platinum group metals, which are certainly more than one element. But the country has, worked with its international partners in industry and others, including Chris, who's going to present next, and, have offered up their own expertise to help winnow this list down. And so this is a list that NRCan has produced of what we're currently considering those elements that are certainly essential to our economic security. They're fundamental, many of these, to our transition to a lower carbon economy. And they've been identified as a key resource for our key partners. And in large part, this has been really driven by discussions with the US administration about trying to actually find these resources closer to home. So, if you look across the country, Canada, like I said, we certainly do have plenty of these resources. And, going back to the very beginnings, of the GSC in 1842, we've been running around all over this country trying to discover new mineral resources. All the blue dots on this map show, for example, various advanced projects where we've got a whole wide range of these different critical metals. But it's really essential to note that, these are advanced projects where companies are trying to bring deposits into production. But that timeline, and, this comes back to cumulative effects, and environmental assessments can be decades in some cases. And we've known about a lot of these deposits for decades, and still they're not actually in production. So, that the lag between, our current need and when we might actually be able to produce metal from some of these deposits could be significant. And it's only in the areas that are shown in green, that's where we have existing mines of critical metals, and we've got smelters or refineries. And in some case, for example, like rare earth elements, we have no refineries at present in the country. And I know some provinces like Quebec recently have announced an intent to try and produce that domestic capacity, but that will be an absolutely key component to us transitioning from having these resources into actually monetizing these resources and actually trying to become not just an exporter of these materials, but adding that value-added component to developing these resources. So just before I get into our research in the second half of the talk here, I just wanted to talk about a couple of key challenges. We all know the world population is certainly not slowing down anytime soon, perhaps unfortunately because of COVID it has in the last 12 months, but it's forecast to reach about 9 billion by 2040. This push for a lower carbon society, people moving to the cities and everything, is dramatically increasing the demand for minerals and metals. And like it or not, it's geology ultimately that determines where these mineral metal deposits are. Unfortunately, and a good example would be something like the Congo, we don't control where these resources are. And so we do have to be concerned with places that might have somewhat lax environmental standards, dealing with social issues, or simple land use constraints. That's been a huge portion of part of the reason why the US has not been able to produce a lot of these resources domestically, is that, there are significant concerns over private land, areas that have been protected, and that really puts constraints on where you might see, for example, new mines developed. A lot of groups have also suggested that substitution and recycling might actually help solve this problem significantly. There's no doubt that it definitely plays a crucial role, but for many metals, it's not going to be enough to meet the increase in demand over time. We have discovered the easiest deposits, over time, and a lot of places. For example, if you go to some mines in Quebec, these are developed kilometers underground, and so we're going deeper to get to these metals, and the rate of new discovery is just not keeping pace with how quickly these deposits are being exhausted. So just before I talk about sort of our research at the GSC, I wanted to highlight what role the GSC plays in the mining life cycle. So I think out there somewhere, I think I saw Aruna Dixit's name on the call today. Aruna, she coordinates a lot of our environmental assessment work at the GSC and reaches out to various experts across the country to get people involved and looking at environmental assessments and that. And that's really an overlap where my own work sort of plays a role. But the GSC is also really involved in things like, pre-exploration in the mining life cycle. Exploration is obviously a huge portion of what we do under programs, certainly, like GEM and TGI, establishing the framework geology and doing things like geochemical surveys, geophysical surveys, developing models of how our deposits form and where we can find these resources. And then we're also involved in things like baseline environmental studies, providing information. Most of my own research goes into this type of work, providing a better understanding of how these deposits might weather in the environment, what water quality, sediment quality, soil quality might look like. And then it's really, we don't do that much in terms of operating mines. And this is really, where there's overlap in some of these different areas with our colleagues at CanMet Mining. Also part of LMS these days, but they are much more involved in operating mine sites and work much clearer, work with industry on how to best extract resources and that. And the GSC, again, plays a role after these places, start to close down. We're involved in helping guide this process of decommissioning and ultimately look at long-term environmental monitoring and also dealing with the legacy associated with historical mine sites. So speaking of such things, I wanted to just talk a little bit about our work in Oka, Quebec over the last few years. This is at a carbonatite-hosted niobium and rare earth element deposit. This is work that was recently wrapped up, but it includes a few of my colleagues at the GSC, including Jean Percival, Catherine Van Nance, did a lot of mineralogical work on these deposits, as well as Alec Deborah, who's a hydrogeologist and has done a lot of stuff on the groundwater component and other mine wastes at this site. So we knew that Canada certainly, has lots of these technology critical metals, including niobium rare earth elements. In fact, other groups like the Canadian Rare Earth Element Network have talked about actually producing maybe even as much as 20% of the global supply in the future. But it's crucial to note, I mean, there are no operating rare earth element mines in Canada at present. We know with certainty that mining of these elements has led to environmental degradation in some places, but there's comparatively very, very few published studies out there relative to other commodities that we know much more about. So, for example, things like copper, lead, zinc, or even gold mines, we really don't know that much at all about the environmental effects, for example, of rare earth element development. So we wanted to do these studies to better help industry as well as regulators and our other federal colleagues to be able to predict the environmental effects of developing these deposits and ultimately to support the development of better environmental guidelines. So as far as rare earth elements, I'm going to just focus in on that for a sec. There are two main deposit types in Canada. One are carbonatite-hosted deposits. So these are a relatively unusual type of igneous rock that are composed of more than 50% carbonate minerals. So they're mostly made up of minerals like calcite and dolomite. They are enriched in a wide variety of what we call incompatible elements, including rare earths, niobium, tantalum, and also fluorine. And they are currently the main economic source of rare earth elements as well as niobium around the world. In contrast, we also have alkaline intrusion-related deposits, and we've got a few big examples like Nechalacho, Kippawa, Strange Lake in Canada, and these are especially enriched in things like heavy rare earth elements. And so these ones are especially interesting for producing some of these rarer metals that are especially important for modern technologies. So if we look at a map of where these deposits are across the country, this was produced a number of years ago as a part of the sort of CanMet-led Canadian Rare Earth Element R&D network. And the red stars on here, there are 14 different rare earth element projects at various levels of development. It's important, again, none of these are actually producing rare earth elements yet, although there is an interesting partnership that's just about to start in the Northwest Territories at Nechalacho, where this group has partnered with a company to actually produce some rare earth elements and we'll ship these elsewhere for production. So that would be the first in the country, but there's certainly a long ways to go. And then we've got other niobium projects. I mentioned Niobec. This is a current niobium producer here in Quebec, but we've got other large deposits, including one in BC, where companies would like to produce these resources as well. Our study is focused here, shown in green, in Oka, Quebec, where there was a former mine site that operated from 1961 to 76. It used open pit and underground mining to produce niobium over time. And in addition to being a niobium deposit, the rocks there they're enriched in things like rare earths, certainly. And some of the main environmental concerns from this deposit type, this is really what we were trying to address with our research. This type of deposit is also relatively enriched in things like uranium, thorium, as well as fluorine, and high radon levels have also been associated or have been measured in some of the local residences there. So there's been companies that have proposed coming back in these days after the mine is closed to even reprocess some of these historical wastes for rare earths. This is definitely not popular, as you'll see in a second, and so the province has actually looked at developing reclamation plans for this site. So this is an air photo taken in 1965, and what you can see, this is actually the outskirts of Oka down here on the lower right. At the time, there was two large open pits that were mined. These are waste rock piles that are shown around the perimeter of the site itself. There was a mill here, and if you look carefully, what you can see is they actually have a big tailings impoundment here where they've created a couple of berms to hold the tailings in, but they actually flooded a former apple orchard here, and the surrounding area, is this beautiful agricultural landscape and that. So, it was interesting. They obviously decided that this was what they wanted to use that land for at the time and just infilled this area completely with tailings and other mine wastes. Now, this mine, as I said, it closed down in 1976, and so the next slide shows the exact same view. but this is in June 2017. And so if you look, what you can see is that down here, the two open pits have flooded. The waste rock itself is largely revegetated. And here's the tailings up here outlined in yellow. There's drainage that comes off on a couple of different directions from the waste rock and tailings. And then there's also a pile of somewhat radioactive slag up here near the tailings. And so, you know, these just going back and forth, you can see basically how this site has changed over time. And these pits in particular, one of them is about 40 feet deep, the other one's about 40 meters deep, the other is about 100 meters deep. So it presents a really nice opportunity to understand what would a site like this look like after several decades of weathering post-closure. It gives us an ability to understand what these deposits might look like if they were mined in the future. So we've used a variety of methods in our studies here, and this is just, I'll run through this quickly. I didn't want to go too far over time here, but you know, we look, for example, at the geochemistry and mineralogy of the waste rock, the tailings, and various secondary phases that host these elements. We've done a lot of work on groundwater. Alec is really leading a lot of that work, and looking at mine waste seepage. And my own work in this case focused on the pit lakes at this site, really to understand, you know, how these have evolved over the decades and look at the controls on things like trace element or radionuclide mobility in those waters. So this is what this site looks like. Here's the tailings here, so a fine sort of sandy to silt-sized material. The waste rock is actually a bit unusual at this site. It's big and blocky as you'd expect, but it also weathers very, very quickly relative to most other types of mines because it's composed of a lot of calcite. There is a radioactive slag present on the site called ferroniobium slag, and unfortunately, like a lot of abandoned mine sites, there's a lot of garbage around, and you see things like milling reagents and other things. I'm going to skip over this pretty quick, but I just wanted to highlight that one of the key things about the slag here is that it is very, very pure in iron and niobium, that the product they were producing was very pure in iron and niobium, but everything else went into this slag. It was basically a pyrometallurgical process at high temperature, and so the slags have quite high thorium and uranium, but are also quite enriched in rare earths. And so this is why there has been some interest in the idea of reprocessing some of these wastes and potentially also reprocessing the tailings for their rare earth element content. I don't think it's going to work certainly for this site, but it is certainly the idea of extracting value from that waste is not a bad idea if you're looking at those sorts of resources. So we've looked at the mineralogy. Gene has led a lot of this work, and the tailings are more than 90% calcite. We've studied the mineral hosts for elements like uranium, thorium, and rare earth elements. And I'll let you go through this at your leisure in some of the slides, just the details. But one of the key things is that, you know, we've got a fair number of sulfide minerals that occur, for example, in these pods in the tailings, so minerals like pyrite and pyrrhotite, but any acidity is quickly neutralized by all this calcite that's around. And so, you know, certainly acid mine drainage is not an issue, but that does release other elements, including rare earth elements, to local surface and groundwaters. In the slag, we also, you know, there's mechanisms by which you could release things like thorium and uranium, and those might certainly be released to the environment over time. And Alec and Gene have done some studies using various leach tests to characterize those processes. So, you know, this is, we've done a lot of detailed mineralogy on things like the original ore minerals, as well as secondary weathering phases here that host elements like cerium and uranium, and then cerium, lanthanum, and neodymium. And one of the elements that's interesting here in the groundwater is actually fluorine. If you look carefully, the tailings, this plot shows tailings going down to, say, 20-meter depth versus sulfate concentrations. And so even though these things are not acidic, they still release a fair amount of sulfate to the pore waters, as well as fluorine, and considerably in excess of the drinking water limits. We also see this if you plot, for example, the fluorine content versus the fluoride content versus potassium. It looks like it's actually elements, minerals like biotite, that actually control this release of fluorine. And so, you know, this sort of information, whether it's fluoride contents, rare earth element, and mobility, this is the kind of information ultimately that we can help to communicate to regulators as things that people actually have to keep track of when they're trying to predict the environmental impacts of mining a resource like this in the future. I'm just going to skip over that slide. I just wanted to show you some pictures here. This is what the pit lakes actually look like. And one of the things we did here was actually seasonal sampling. And I mentioned these pit lakes are very, very deep. So we're really trying to understand how these elements cycle in these pit lakes over time. And so we went out with a Zodiac, for example. So my colleague Lori sampled waters in the water column, did some profiling down through the water column in various seasons, and then also deployed data loggers in the waters. And this allows us to actually measure things like temperature, depth, and conductivity in situ in these waters. And so one of the key things we were able to observe there, this is just sort of some bathymetry showing these pits, but what you can see is that you get, for example, variations in temperature. You know, as you'd expect, the water is very warm in the summer, very cold in the winter, high dissolved oxygen sort of near the surface. But as you go down in the deeper pits, there's what's called a chemocline at about 30 meters down. And this is a depth in the pits below which there is very, very little overturn in the waters. The waters basically do not mix regardless of the season, and you can get very, very different water quality in these deep waters. And so the reason that this is important, as you can see, this is specific conductance here, it shows what's dissolved in the water, is you can get very low water quality with high concentrations of dissolved elements. So things like manganese, they go from almost below detection, close to the surface, to greater than about 10,000 micrograms per liter in the deep water. But you get other elements like uranium, lanthanum, fluorine. And so these deep waters can cause water quality issues if they are to mix with surface water or if there's seepage downstream. We've also characterized the major element contents of these pit lake waters. They're all, for example, they're fairly neutral, but very, very high dissolved concentrations of things. And so the reason this is important is that if you're someone that is trying to predict the effects of this water on fish or other aquatic biota, it's really, really crucial to understand what this water quality looks like. And it also affects the mobility of other elements like rare earth elements. So I realize I'm running a little long here. So the last few slides I want to share with you are actually about our more recent studies in Cobalt, Ontario. And this is where we are specifically looking at cumulative effects. And so this is a project that's led by Alec Deborah and includes, again, a few of our colleagues, including Jennifer Galloway in Calgary and Paul Gammon in Ottawa. And the reason we've decided to start working in Cobalt is that this is a district, very different geology, but where rich silver veins were actually discovered back in 1903. By 1911, Cobalt was actually the third largest mining center in the world. And the last mine shut down there in 1989, but it really unfortunately left quite a mess behind, dozens of abandoned mine sites, 18 uncontained tailings disposal areas, and very, very high arsenic, nickel, and cobalt contamination in the surrounding area. The challenge is that there is now this new exploration boom that's focusing on cobalt for rechargeable batteries. And so, you know, if you look at the old history of this site, and the town has done a wonderful job of highlighting this, you know, you see pictures of people with their silver bars, you know, all these black and white photos of all sorts of impressive looking mining operations going back a century or more, but also plenty of mine sites shown here in this map in red, as well as tailings deposits all over the place. And, you know, the town has really celebrated this history. It's actually a National Historic Site. They've done a wonderful job of highlighting this mining history. But then there's the flip side. If you look in the news, this is where we see cobalt seen a lot of discussion. A couple of years ago, the CBC had announced that these abandoned mines could boom again due to battery demand. Earlier this year, First Cobalt, a company that has a refinery in the area, it's the only cobalt refinery in North America, has announced their intent to start up this new refinery, and the federal government has helped to give them some seed funds for that. And other companies are actually interested in going back into this camp and maybe even mining elements like silver again. And so we've got all of this renewed mining industry in a watershed that is very heavily impacted. So, you know, this is really sort of where I'd like to end the talk, and really to make this connection with cumulative effects is, you know, our current abilities to regulate resource development in these brownfields or historically impacted watersheds is challenged. Mining companies, you know, they are not enthusiastic about assuming environmental liabilities. You know, it makes lots of sense that we would want to reprocess old mine waste, for example, for their cobalt content, but not if, you know, a company is required to inherit, you know, potentially a multi-million-dollar environmental liability at the same time. So, you know, we really need a better way of approaching environmental assessments and tools and techniques to separate out the effects of old mining versus new mining, and figure out whether or not we can, you know, protect local water resources at the same time that we're trying to develop these new technology metals. So these are the questions we're asking. You know, how do we assess the environmental impact of a new mining activity from, for example, a company like First Cobalt, you know, from an operating mine that was operated 100 years ago. One of the ways we're trying to do that is to look at the pre-mining signature, the sort of concentrations and things like soils and sediments and vegetation before any mining, as well as modern day baselines that will give us something to measure new development activity against. The other thing is that Mother Nature has taken hold in these areas. So there are some areas that have actually started to reach some sort of new equilibrium. They might not be the healthiest environment, but a lot of these wetlands are thriving. And there's lots of species living there now that, you know, need to be considered when you're talking about redeveloping an area. And so we're really trying to fine tune things like sediment coring and other techniques, groundwater studies, you know, to really try and tease out these baseline effects and figure out the best way of measuring these new impacts in the future. So, you know, I think this is the last two slides. We've done a little bit of pre-COVID water sampling. We went out, sampled some cores in the area, and certainly Gene, Percival, and others have done some historical work in the area. And we're collecting cores, really, you know, to look at elements like arsenic, cobalt, mercury, nickel, and antimony, you know, to understand what are these concentrations like now and how might they change in the future. So I'll leave it there for today. This is the last slide was actually some drilling that we did just a couple of weeks ago. Like most others, we've had to contract this out to people that lived in the area because we can't travel up there right now. But we're hoping that this will give us a better understanding of the mineralogy, the geochemistry, and ultimately the environmental impacts of these sorts of mine wastes. Anyways, thank you very much.
Thank you for your presentation, Michael. The floor is open to questions, so feel free to either type them in the chat or raise your hand. I think if you go to the participants, there's the raise hand button there, or it might be in your reactions at the bottom of the Zoom call. If no one has any questions to start, I have one that I wrote down. So you mentioned that there's no operational mines currently for rare earth metals in Canada. And I'm wondering, I mean, you're mentioning environmental risks aren't like well known yet, and you've done some work in understanding those and studying that. But is that the main reason why you think rare earth metals aren't being mined in Canada right now?
That's a great question. And actually, the answer is partially, but the main reason, to be honest, it's not so much that we don't have these resources. I mean, you know, there's been plenty of geologists and explorationists that have done a great job of discovering these resources. But the biggest barrier is the actual processing and the separation of one element versus another. One of the biggest problems is that the minerals that contain the rare earths are very unique to each individual deposit and potentially might require quite different processing techniques. And so if you have an element, let's say for a big deposit like Strange Lake, the minerals that contain those rare earths are quite complicated, and the metallurgy, unfortunately, has not advanced to the stage at which a Canadian company right now could easily separate out a whole wide range of, say, 10 different rare earths from one another, and do that in a manner that's cost competitive with the Chinese, that have very different regulations for things like environment, issues. And of course, they've been at this for years and years and probably aren't all that particularly anxious to share some of their trade secrets with other companies as well. So that, as far as I understand, is the main barrier. And there's been a huge amount of work on that through this CanMet-led Canadian rare earth element R&D network. But my understanding is there's still quite a ways to go before we get there.
Thank you for that answer. We have a question in the chat from Ann Ross. I'm not sure what the first name is, but is there a plan to quantify the metals that are in the tailings? In other words, coming up with an inventory of resources?
That's also another really good question. And the answer is yes, that's already started in some respects. So if you look at elements like, let's say, for example, for rare earths, again, another part of this, Canadian Rare Earth Element R&D network, I think the website address is rechromite.ca. They actually have been looking at not just primary sources like new mining, but also secondary sources of these elements. So quantifying the concentrations in mine waste, but also a whole lot of other products. So things like coal fly ash and other waste products in that, to see whether or not we could produce rare earths from these things. And there is, I think, going forward, more of a need, and Chris might mention this in his presentation too, to really understand the concentrations of critical elements in a wide variety of different waste streams. And I think there's a huge potential for growth as far as that goes, because even if you, for example, are here in Nova Scotia, we had a long history of gold mining historically, but there could be other elements in those mine wastes out there today that were not of interest to us 100 years ago that might serve as a resource if we were able to find a way to do that. So again, CanMet has a program called Mining Wastes from, as Resources, and a few of us have been directly involved in those studies to look at, could we extract elements, like cobalt and other things from tailings and waste rock, as opposed to having to dig new mines and produce new mine waste in the process.